To begin with, on the verification of the Faraday's law of electromagnetic induction, here is a setup. Here we connect this one coil, this tons of wire, this particular one. We connected it to this ammeter, which is having a rating of milliamps, so such that you can see the deflection easily, because the current generated or the voltage induced here is very small depending on the number of turns of wire according to this law. This N stands for the number of turns of wire. When the number of turns of wire, if we add up these two turns of wire together, you will find out that the EMF induced on this coil output here will be higher. So looking at this is just to demonstrate this Faraday's second law of electromagnetic induction. So meaning that if we are to move this magnet across these turns of wire, which is a conductor, it will induce an EMF or current into this, which you can tap from these terminals of these coils. So looking at this is the one end of this. This is the one end of this coil, and this is the second end of this coil. So why these are two separate coils. So looking at this, we deflect this. When you make this to rotate, to move, you will find out that it is deflecting. That is to say, if what happens here is the rate of change, if you increase the speed, you can see this gets to a point, meaning that what is given out here is way higher than what this ammeter is rated. So it hits to that point. But when you use smaller speed, that is the rate of change of the magnetic flux dropped, the current induced on that coil remains smaller, as you can see, about 1.5. But when you increase the speed, you will get a higher current. Now, because this experiment you cannot truly see the action of the two coils, I will demonstrate this using this voltmeter, which is rated in a normal volt and not in millivolts.